finding maxima and minima for models of situations is a fairly straightforward algorithm, though in practice I will say it is a fairly difficult exercise. So the way you're going to do this is the way you kind of solve any word problem, except we're just going to apply calculus. The first thing you do is you identify givens. So you say, all right, what does this problem actually ask me, or what does it give me? Does it give me equations? Does it give me that it's looking for a geometric object? What does it give me? Does it say you start with $50? Who knows? What do I start with? The second thing you want to do is identify outcomes. What are you trying to solve for? At the end of the day, are you trying to solve for the maximum profit? Are you trying to solve for the minimum time that you spend? Think about a GPS. You can optimize a GPS for the shortest path, but you can also optimize it for the least amount of traffic. You can optimize it for the lowest cost by factoring in toll roads and things like that. So what are you trying to solve for? The next thing you want to do is write a primary equation. So what does that mean? That usually means to write an equation that is related to this too. So if you are trying to maximize the volume, you need to write a volume equation. If you are trying to minimize a cost, you need to write a cost equation. That's what your primary equation is. Now, the fourth part is this is hard enough. This is really hard for a lot of people new to this. This is maybe just as hard. The idea is what you would like to do is usually end up with a jumble of variables. You might end up with, if it's a volume equation, you might end up with a length, a width, a height. You might end up with several things. However, what you have to do is you have to reduce this to a function of one variable. What we do this by employing what are called secondary equations. Secondary equations are extra constraints on the problem, or something that you can use a little bit of cleverness and manipulation to exploit so that you can reduce an equation of multiple variables to one of a single variable. And once that's done, again, this is one of the harder pieces, then the calculus techniques are fairly straightforward. What you're going to do is you're going to define a domain, because sometimes the domain is everything, but in practice it really isn't. And once you define a domain, then you can employ the techniques of calculus to find maxima, to find minima, and then if you do define that domain, make sure to check your endpoints. Say, okay, well, it's got to, if I say it only starts here and here, what I might find is a critical point, but that critical point may actually still be less than one of the endpoints. Think of a curve where you have 2 points here, and it goes down and down and up to that second endpoint. Well, at the endpoints, it's actually higher than that local max, but you won't be able to find the critical points on the edges, so you still need to evaluate the edges of those domains. It's always very, very important. Anyway, so let's do an example here. What we've got is, let's say the problem statement is find a point on the curve y equals 4 minus x squared that's closest to the point 0, 2. So 4 minus x squared is a downward opening parabola, like so. That's not really, it doesn't really look like a parabola, it looks more like a circle, but it's supposed to be a downward opening parabola, and there's this point 0, 2. And we want to find what's the closest point to that. So actually I haven't solved this, but this is a really good example because 0, 2 might be what's called the focus of a parabola. If you've ever seen what's called a parabolic microphone, one of the cool things about parabolas is they have a focus, and any incoming ray to the parabola is automatically kind of reflected off the parabola to the focal point. And so by doing that, you can take a parabolic microphone, and any incoming sound that would hit, the parabola, the paraboloid shape there, is automatically directed towards the microphone. So it allows you to really catch sound and bring it in. It's a very, very clever technique. And so, but you might want to figure out, okay, what point is actually closest? What point is going to have the minimal distortion? And so if that's true, then you might want to define you may want to take some extra care when making that piece to really get crispness. So anyway, that's a little bit of extra flair there, but there are practical reasons we would want to do this. So to do that, we could take this distance formula. We'll say, all right, well, what we got to do is figure out some xy point such that x minus 0 squared plus y minus 2 squared all under the square root is a minimum. Notice in this case, it's the closest to, so I know I'm trying to get a minimum here. But there's a little bit of cleverness. See, again, this is where the techniques come in. This is technically the distance formula, but when this thing is minimized, it's actually the inside that's minimized, right? Because if all you're doing is squaring it, that's just a bigger number on the inside. So one clever trick when you're taking the distance formula is you don't have to minimize the square root of what's inside. You just have to minimize what's inside that square root. So just this piece. So we're going to call this our primary equation, when normally you might call this your primary equation. Let's do this one. So that's a really interesting technique. Now, a secondary equation is this one. It was given to you. Because our primary equation is a function of two variables, x and y. Well, that's no good. I need it to be all in one variable. Well, if I take this secondary equation, anywhere I would see a y, I can plug in 4 minus x squared. So now I have a distance function of one variable. By simplifying that one step, I get this equation, and by simplifying it further, I get this sort of semi-quadratic equation. By doing that, I say, okay, well now I have some equation. Great, good, great, grand, and wonderful. Let's see if I can find a critical point of it. If I take its derivative, I get this function here, which I can then factor into 2x squared minus 3. So if I set this thing equal to 0, remember critical points happen when the derivative is 0 or fails to exist, and this derivative will never fail to exist because it's polynomial, then plus or minus the square root of 3/2 are possible critical points. Now you may ask yourself, are those valid critical points? Well, if you think about what the domain is, if you look up here, technically speaking, the domain is all real numbers, because the parabola never, doesn't stop going. So what you can do is you can constrain it if you wanted to. You don't have to do this, but you could constrain it and say, okay, well, I'm only going to concern myself with the points that are positive for y, or at least non-negative, because once I know I cross that axis, I know I've gone too far. Well then, if that's true, then we could say, all right, as long as x is between -2 and 2, that'll be our domain. Again, you don't have to do this. So if I've got these critical points, what I can do is I can apply the second derivative test. I take the second derivative here, I get -12x squared minus 12, which I can then factor into those pieces, or I could leave it as this. It would be fine either way. Probably actually better to leave it as this. If I evaluate the second derivative at negative square root of 3/2, I actually get the same value as I get for the positive square root of 3/2 because of the way that that squares out the negative. And in each case, 3/2 minus 1 is greater than 0. So both of these derivatives are greater than 0. That means we're concave up. So if we're concave up, that means that value must be a minimum. So both of those are local minima. Given the fact that we have two local minima, the only thing left to do is we need to check those endpoints, just to be safe. So if I plug in -2 to the original distance function, or if I plug it into here, I get the same thing as if I plug in +2, because they would all get squared away. You get +8. If I plug in these values, I get square root of 7 over 4, which tells me that the distance there is lower, which tells me that these values, these 2 points, are my actual minimum. So if we go to these points and those points. Those 2 points on each side of the parabola are going to be your minima. I didn't plug this into the original parabola. We could. You would get the point negative square root 3 over 2. And then I guess it would be 5 halves and square root of 3 over 2, 5 halves. Those are your 2 points, and those 2 points are the closest to 0, 2.